Hello everyone, I'm Sophie, a data management specialist based in Tokyo. Today, I'm going to talk about how Cloud Spanner helps gaming companies modernize their gaming application and better players' experience. ML can help you predict many things today, and it's amazing. But one thing it cannot predict is the success of a game. So what are we trying to solve here with our database solutions? Unpredictability. Compute is very easy to scale. You need more resource, you add more server. When a game gets a lot of players, database is usually the bottleneck because legacy DB like MySQL are not designed to scale horizontally. How did gaming companies solve the database scaling problem? Well, by using a technique called sharding. The first one shards data by player's name. The more you will split the DB, the more players your game will handle. Second one is realm sharding. This is typical in MMORPG, where you create new parallel worlds when you need to handle more players. If a single database server can handle 10,000 players, then they have to manage 100 servers for each million players. Last one is platform sharding, where you will separate players' population by platform. What if you could simply scale your game backend? That's where Cloud Spanner comes in. Cloud Spanner is the first enterprise-grade, globally distributed, and strongly consistent database service built for the cloud, specifically to combine the benefit of relational database structure with non-relational horizontal scale. What are the key benefits of using Cloud Spanner for gaming application? Manually sharding makes it difficult to maintain consistency and transactions across shards. Cloud Spanner gives you relational data and horizontal scaling. It optimizes performance by automatically sharding the data based on the load and data size. Customers who are using our DBMS want more power and are considering a scalable non-database. Spanner allows them to keep their relational data and can be scaled. Cloud Spanner has no planned downtime for maintenance with fully automatic data replication and server redundancy. And it delivers up to 5 nines of availability in multi-region instances. Also, Cloud Spanner users can make a schema change while serving traffic with zero downtime. With Spanner in a multi-region configuration, any update is automatically replicated across regions so that you don't have to add extra logic for that in your application. Let's take a look at some examples of companies using Spanner. Niantic learned about how Google Cloud can help gaming companies ensure they have enough scale for a surprise hit with Pokemon Go. Pokemon Go widely succeeded the team's capacity estimates, and they used Google Cloud Data Store to scale to over 50 times their predicted worst case scenario. After a few years, Niantic migrated from Data Store to Spanner, which reduces their operational cost and improved latency. Another example is Dragon Ball Legends from Bandai Namco, with Cloud Spanner as a backend DB. BNE focused on developing an amazing game instead of spending time on database, capacity planning, and scaling. By using a fully managed scalable database, they drastically reduced the risk related to human errors as well as operational overhead. Let's take a quick deep dive into Spanner and some of the benefits of cloud native. The Google network offers better reliability, speed, and security performance as compared with non-deterministic performance of the public internet or other cloud networks. Spanner's capabilities are augmented by our global private fiber optic network that stitches together all of our services and allow us to provide low latency backend. Spanner has two types of instances, regional or multi-region instance. The diagram represents a two-node regional instance. For each node, Cloud Spanner will create three synchronous replicas across zones. Each zone in the region contains a few replicas of the database. With multi-region configuration, Cloud Spanner will create up to 9 replicas for each node. These additional replicas enable you to read data with low latency from multiple locations close to or within the regions in the configuration. Here, I'd like to highlight the new multi-region instance configuration in Asia called Asia 1 with Tokyo, Osaka, and Seoul region. It's often mentioned that true time is essential to make Spanner work as well as it does. So what is it and how does it help? True time is a way to synchronize clocks in all machines across multiple data centers. The system uses a combination of GPS and automatic clocks to give an accurate source of time for all Google's application. Cloud Spanner assigns a timestamp to every read and write transaction. Different nodes can make decisions about the order of transactional operation made from other nodes by simply comparing these timestamps. It enables applications to generate monotonically increasing timestamps, which allow the system to behave as if all transactions were executed sequentially. Even though Cloud Spanner actually runs them across multiple servers in multiple data centers for higher performance and availability. It's a combination of Google Fast, redundant, global network, and TrueTime makes Google Cloud Spanner external extension possible. So how do we spread the data to Spanner nodes? Each table in the database is broken down into several what we call splits, used range of the primary keys. All of the data in a split is physically stored together in a replica. And Cloud Spanner serves each replica out of an independent failure zone. For example, this table is separated into 3 splits used range of the keys. In reality, the number of splits can vary according to the amount of data, and the splits are rebalanced dynamically depending on the amount of data and load. So for the 3-node instances we saw previously, it could be managed like this, going back to our original scenario, with each node handling 3 of the splits. But remember that the table and the nodes are replicated across 3 zones. How does that work? Look across the 3 zones. Each split is replicated in all 3 zones. Use Paxos consensus protocols. One of the zones is determined to be a leader. The leader is responsible for managing write transactions for that split, while the other replicas can be used for reads. Every write operation must pass a majority quorum vote. For different splits, different zones can become leaders, thus distributing the leadership roles among all the Cloud Spanner compute nodes. It's using the distributed mechanism of splits, leaders, and replicas that Cloud Spanner gains both its high availability and scalability. Let's talk about what scalability looks like in practice. By increasing the number of nodes, you add capacity. A node can handle around 2,000 writes per second and 10,000 reads per second. Imagine we're approaching launch day for our game, and based upon the throughput capability of a Spanner node, we've determined that we need a 3-node cluster for a total potential threshold of 6,000 writes per second and 30,000 reads per second. Based upon our best estimates, we've determined that 3 nodes of Spanner should be sufficient for anticipated launch day load. You can configure Cloud's performance capacity with a number of nodes. Shortly after launch, the game goes viral and traffic surges, pushing the Spanner instance past performance thresholds. We can easily go in and add an additional node to our instance. Once a node has been added to the instance, the nodes add their pointers to the splits. Node is moved. Now, with the additional node, we have a new performance ceiling of 40,000 reads per second and 8,000 writes per second, and performance begins to stabilize. Crisis averted, and with a minimum amount of fuss. No frantic re-architecting, resharding, replatforming of the data. Behind the scene, this is Spanner dynamically resharding the data. After some time, performance returns to pre-search levels, and we find ourselves with significant additional capacity. To help save cost, we decide to edit the instance and remove the additional node that had been added. So far, I have described some key concepts and advantages of Spanner for gaming customers. Hope I could give you a quick overview regarding how Spanner can help gaming applications with strong consistency, dynamic scale, global data distribution, and live operation. Cloud Spanner has been tremendously adopted in gaming industry. And I'm so excited to have one of our very cool customers, Cropla, here today to share their story with Cloud Spanner.
Thank you, Sophia. Hi, my name is Taka, and I'm a software engineer for a Japanese game company called Koropla. I will take over from here and briefly talk about how we use Cloud Spanner in our game, Dragon Quest Walk. Before I begin, please allow me to do a brief introduction about the game. Dragon Quest Walk is part of a long-running Dragon Quest series owned by a company called Square Enix. And here are some screenshots of what the actual game looks like. This is a role-playing game where you walk around and fight virtual monsters in a real-world locations using GPS and AR on your mobile devices. Here are some numbers to give you an insight of how much data we process every day. So the game was released in September of 2019 in Japan, and it has been downloaded over 5 million times just in the first week. Currently, we have millions of monthly active users, which are handled by over 10,000 pods on GKE. And through these pods, we process thousands of queries per second across hundreds of Spanner nodes every day. Here's the agenda for what I'm going to be talking about today. First, I will start by talking about why we chose Spanner. Then, I will talk about how we integrated Spanner into our development. After that, I will provide some tips on how to use Spanner in real-life scenarios. So now I'll talk about why we chose Spanner for this game. There are 3 reasons: scalability, cost, and stability. Starting with the first one on the list, scalability. We used to use MySQL to handle all our user data, and we scaled it by splitting data into horizontal shards. This worked well for a while, but when the numbers of shards grew to double digits, we started to notice some problems with this approach whenever we wanted to scale. Scaling in and out took days to prepare, and we scaled every month. So we would scale out whenever we released a new feature to handle the high traffic, and then we would scale in to save costs once the traffic eased. By switching to Spanner, we were able to do this with one click, and scaling would complete within a few minutes. The second reason is cost. Like I've mentioned in the previous slide, we used to spend days scaling MySQL, but switching to Spanner enabled us to reduce the time it takes from days to minutes, and that reduced the cost of operation quite a bit. Another place we saved costs was from code maintenance. Sharding made the code complex and difficult to maintain. Because the code had to accommodate for things like distributed transactions and replication delays. These things made it costly to add features and fix bugs. But using Spanner allowed us to simplify the code, so adding features and fixing bugs could be done a lot cheaper. The third reason we chose Spanner was for stability. As mentioned by Sophia, Spanner has at least 4.9 SLA, which is phenomenal. When we self-managed MySQL servers, which amounted to hundreds, a small number of them used to crash randomly at a constant rate. And handling these crashes used to cause a lot of grief. After switching to Spanner, we haven't had any of these types of crashes. We've been running this game for 10 months now, and we haven't had any major downtimes. Now I would like to talk about how we integrated Spanner into the game's development. Here's the architecture overview of how it looked like before we started using Spanner. As you can see, MySQL was used to store all persistent data we used in the game. And here's the architecture overview after the integration. As you can see, Spanner replaced MySQL for storing persistent data. You might have noticed that MySQL is still used for shared data. I'll be explaining that later in the presentation. So now I'll explain how we actually did the integration, starting with some background. When we first decided to integrate Spanner into the game, we knew it was going to be a challenge, since the game was already in development using MySQL. So we did some preparations to make sure the transition would be smooth and painless as possible. So here's the process we took to integrate Spanner into development. First, we started with a small dedicated team that ran some basic benchmarks to check the performance. Once that was good, we created a dedicated driver for a PHP framework we were using called Laravel. Doing so allowed us to use the framework's ORM, which also made it possible to use extensions we built in other games. So once the driver was written, we tested the driver by replacing MySQL driver with a Spanner driver on an existing game. This method worked well because we got to see how it performed on real-life scenarios. After that was done, we joined the game development team to educate them through learning workshops. So by doing these preparations, the game development team was able to fully integrate Spanner in about 2 weeks. Now I'd like to give you some tips for using Spanner in real-life scenarios. The first item on the list is handling bursts of access to shared data. So our game had some small sets of data which is shared across all users. These are things like item properties and monster map coordinates. Now, if we access these data in Spanner, we would get what's called a hotspot in the database, which caused latency to shoot up. This happens because all the I/O is happening on one slice of data that cannot be distributed, as you can see in the slide. This is troubling, but there is a way to work around this. The way to handle this kind of data in Spanner is to add a column with a shard number and insert copies of the data with shard numbers assigned to them. Then what you can do is have the app select one of the shards at random and add that to the query, and that will distribute the load. This implementation works, but unfortunately, we did not use this solution in the game because we figured it was too difficult to implement into the framework at the time. So our actual solution to this problem looks like this. Yes, we decided to use a self-managed MySQL instead, since MySQL can replicate and scale out easily if all you have is a small set of read-only data. The next thing I would like to talk about is handling launch day traffic. So as described earlier, when there is high load on a split, it adds more boundaries to distribute the load. This works well in normal scenarios where there is a gradual growth on load, but this was not what we expected to happen on launch day. No, what we expected to happen on launch day was thousands of users registering in a span of a few seconds. So we did a simulation of launch day traffic by ramping up game bots that mimic user behavior, and this is how it turned out. Immediately after we started the test, the CPU usage shot up and latency of the queries increased to a point where it was unplayable. The reason this happened was because Spanner could not make the splits fast enough to handle the huge amount of data that was being inserted. So we concluded that in order to make Spanner handle this massive traffic, we needed to make the splits before the launch. So this is how we resolved the issue. We fed Spanner just enough queries to allow the load-based split to trigger and increase the number of queries gradually until there was enough splits to handle the desired QPS. This was a tricky process because if we fed it too many, the CPU would starve, which slowed down the splitting process. But if we gave it too little, there wouldn't be enough load to trigger the split. So we had to monitor the metrics constantly to ensure that we fed Spanner the right amount of queries. Since this was a tedious task that took hours to complete, we made a warm-up app that automated the whole process. And here's an illustration of what the whole process looks like. So in addition to what I've just described, There are two things you should be aware of when doing a warm-up. So number one is do not drop the tables after the warm-up. In most cases, you would want to delete dummy records that were inserted during the warm-up, but don't do it by dropping the tables because that will also clear the splits. You should delete individual records instead, since that will allow the splits to remain. So the second thing you should know is to warm up 24 hours before the launch. Spanner seems to merge the splits if they aren't being accessed for over 48 hours, so make sure you warm up your database 48 hours prior to launch. So the last thing I want to advise is how to scale in. So in this game, we scaled in and out fairly often based on how much traffic we're expecting for the day. Scaling out is simple since all you have to do is increase the number of nodes in the UI and wait a few minutes for it to be deployed. Scaling in, however, is a bit more tricky. When we scale in by reducing the number of nodes too aggressively, we notice that the latency increased for some users. These latencies range from a few milliseconds up to something like 30 seconds. So we resolve this issue by forcing Spanner to time out in 3 seconds and return a retry response, which asks the client to retry after a few seconds. In addition to that, we now reduce the number of nodes in small intervals, since the latency seems to be proportional to the number of nodes we reduced. We managed to minimize the delay enough. No retries occurred on the client by reducing the number to 1 node per 5 minutes. So the takeaway here is, don't try to reduce the number of nodes in one go, but reduce them gradually in small intervals. That's all I have for you today. Thank you for your time. Handing it back to you, Sophia.
Thank you, Taka, for your great story. For the next steps, we have a few more sessions about Spanner. So if you have time, please watch them as well. Also, we have demo and quick lab about Spanner as well. Please try them out. Okay, that's all for today from us. Thank you for watching.